Hi there guys, and welcome back to another online tutorial for Organic Chemistry 2. We're going to continue the NMR series today, so let's go ahead and get started with that. So last time we talked about how an NMR instrument actually works, and we use a very large magnet, and we send nuclei into the magnetic field, and we align those nuclei, and we basically hit them with energy and we flip their spin state. So if you have any issues with that, go ahead and go back and check out the original video that introduced us to NMR. So the biggest concept I want to talk about today is that of chemical shift. All right, so this basically tells you where along the NMR spectrum do I expect to see a specific nuclei. So the range that we get down here, the unit that we normally use, is in ppm. You may see some people refer to this as frequency. ppm stands for parts per million, but it's really frequency because what we're talking about is the radio energy that we hit those nuclei with in order to get them to flip their spin state. And then they take some amount of time and they give some energy back off as they relax back down to their normal state. And depending on the frequency of the energy they give off, we are going to end up with signals in different spots. So for a proton NMR, which is probably the most common of the bunch, an H1 NMR, we are going to see a general range in ppm of 0, where you normally would have a standard. A lot of people use TMS, which is tetramethylsilane. And then it goes all the way up to maybe 13 ppms or around there, probably closer to 12. Sometimes you get some signals over 12. Now, ppm is standing for parts per million, and we're talking about the parts per million of frequency at which these protons are basically releasing the energy back as they're on their way back down to the normal spin state. So keep in mind, when we use a NMR, we're talking about megahertz. So a 200 megahertz, a 500 megahertz. A mega, the prefix mega, stands for million. So we're talking on the scale of hertz down here. Now the reason we use ppm is ppm helps us to generalize or standardize, I should say, the chemical shift scale. Because you could have one set of nuclei appear in one area on a given NMR, like a 200 megahertz NMR, and it would appear in a slightly different valued area on a 500 megahertz NMR. So doing parts per million, if you calculate that, will help to standardize and give a pretty general scale that everybody can use interchangeably. So that's why you're going to see ppm down here. Now, a couple important points, and we're going to talk about this in a second in more detail. Going this way, so the further I get towards the 0, this is known as the upfield region when we are discussing NMR. And down this way, we are going to talk about the downfield region. So you may hear me say that. Your instructors may say upfield, downfield. They're referring to these particular positions. There's no exact split, but you usually talk about it in general terms. So you'll say, oh, this proton or this signal is found far upfield because of X. And we'll talk about what X is here in a second. Okay? So you'd have, 1 up through 13, and you're going to get signals that occur in a specific spot related to the type of nuclei that might be present, right? So we'll see different lines that are being retrieved here. Now, I should mention that most of these use Fourier transform. So we're talking about FT NMR techniques, which will give you these nice clean peaks. Keep in mind, when we have this, we're really basically, the nuclei are going to emit a wave signal back to the instrumentation that it detects. This will process the wave signal using Fourier transform, and we will get nice clean signals out the other end. So just so we're clear, that's how that occurs. Okay. Now, the concept that really determines chemical shift and where these different protons or carbons or anything like that are going to be is a concept that is known as shielding or deshielding. We're going to talk about both here. They go hand in hand. Shielding and deshielding. All right. So what we're looking at is neighboring are there any real sufficient neighboring electron withdrawing groups? Okay, or anything that has sort of high electronegativity is what we're going to be looking at. So to begin understanding shielding and deshielding, right, let's use a very simple example. I have this nuclei that's aligned here. We'll say that this is for a hydrogen. And going around or surrounding this nuclei is an electron, just like we would normally find for a hydrogen atom. This electron, as it circulates and it basically goes around or takes up space around the nuclei, or where the protons are going to be, this is going to shield, okay? This is going to shield the nuclei from incoming radio waves, and it also shields it, particularly what we're talking about is this shields it from the larger magnetic field, right? So this is the NMR magnet when we talk about the large NMR field. When you have electrons, basically imagine that you have your little nuclei in here. It's exposed to magnetic fields, to radio waves, to all that sort of stuff. And the electron that goes around it can help to shield or protect that nuclei from the magnetic field and the outside influences. So that's the idea of shielding. Now, when you have shielding that's occurring, you are going to have upfield signals. So if something is well shielded, you will get an upfield signal. The further I go downfield, it means the more energy is going to be put in, because as I deshield these electrons, and this is a complicated concept, as I deshield these electrons, they are exposed to the NMR field. And that's going to cause a larger gap in the energy when I get ready to expose them. All right? So in other words, take a look here. Here's my spin up energy state, right? And here's my spin down energy state. And we will say that this is for something that is shielded from the magnetic field. So it doesn't require a huge amount of energy if it's pretty well protected from the magnetic field to make it jump into this opposite spin state. However, if I start to deshield, and we'll talk about how we do that in a second, I'm going to end up increasing the energy jump, because this proton right here, okay, or this nuclei, is going to feel the effects of the magnetic field to a larger extent. And so think of this again just as swimming upfield. If you're in alignment with this large field, it's going to require more energy for you to go against the gradient the more in line you are with this field. So right here, if this is well shielded, it's not too exposed to the NMR field, generally speaking. And so I require only small energy jumps, right? This would be an energy jump, in order to switch the spin states. Because it's not in, I don't want to say it's not in alignment, but it can't feel this NMR field as strong. I come over here, something that's deshielded or has its electrons being pulled away and removed from the nuclei. This is now in alignment, very, very strong alignment with the NMR field here. And so it requires a larger energy jump in order to go against this NMR field. And so therefore, we're going to see that the deshielded is going to appear downfield. Okay, and if you ever forget which is which, keep the D's in mind. Deshielded means downfield, and downfield is to the left side. It requires more energy. Our ppms are going to get higher. We require more energy to make this jump here. So that's really what's going on. So let's take a look at a practical example here. All right. If I have CH3O, C double bond O, CH2, CH3, right? This right here is directly next to an oxygen. Well, this oxygen is most definitely an electron withdrawing group by its inductive effect. So we have a dipole headed in this direction towards this oxygen. So we would say that the protons here, because we're really looking at the H's if we're doing a proton NMR, all right? these hydrogens associated with this CH3 are going to be de-shielded to a pretty decent extent because they're next to an electron withdrawing group right here. So that means that most of the time, and I'll give you a couple of common examples, but most of the time when we find these protons directly next to a sp3 hybridized oxygen, now you could argue because of the resonance here, we could talk about possibly sp2 hybridized, but we're not going to get into that argument right now. If you have any CH3 group, or any group for that matter that has protons directly next to an oxygen, like an ether, an alcohol, something like that, you will end up with a ppm that's going to be on the very low end, around 3, and it could go up to as high as probably about 4.5 ppm. Okay, so you know that if you saw a signal at 1 ppm, it could not be related to this here, because these nuclei are going to be too de-shielded to appear in the 1 ppm region. Okay, the oxygen itself does not have any nuclei, and when I say this, keep in mind we're in reference, it does have a nucleus, but we're keeping this in reference of the HNMR. Carbon, oxygen, so the next set we get is the CH2 here. Now the CH2 is next to a carbonyl, which is an electron withdrawing group. However, it won't be quite as strong as the oxygen that's directly bonded to the CH3, right? Because this is a carbon and the dipole is up towards this oxygen. So there's certainly a pull, but it's not going to be quite as strong. So this guy would probably show up anywhere between 2.5 ppm to maybe, we would say 3.5 ppm. Okay? And I'm giving general examples here when I'm giving this large range. This would really be in probably a smaller range than that. So then I get to this methyl group right here. This is 2 removed from this group. So as soon as we get 2 removed, we're starting to get further away from the electron withdrawing effects, and by 3 removed, we're back to normal. So this is a very immediate effect when we're talking about shielding and deshielding. So this would also be slightly deshielded. This would be pretty well shielded. We wouldn't have too many issues with this, okay? And this group that's shielded, we would say normally this group appears around 0.7 to roughly 1.3, and we would probably say it's maybe around a 1.1 or something like that. That's because we do have an electron withdrawing group 2 spaces away, so there's probably very mild influence here on these protons. If I were to extend this and there were another CH3 group or something like that out here, if this was a CH2, it would get even further when we're talking about that, and then we'd be closer to probably the 0.7 range. So that's shielding and deshielding. Now let me give you some common examples, because if I just throw these up, people kind of see it as being rather arbitrary, right? So if I have just a general R group and I have a terminal CH3, these guys are normally going to be somewhere between, and we just said this, 0.7 to 1.3, depending on whether or not they have neighbors that are electronegative nearby. Now, if it's directly attached, that's a whole different ballgame. We were just talking about the 3.5 to the 4.5 or around there. So CH2 groups, right, that would be found in the middle. If we're dealing with the CH2 group, we would be talking about probably, I'm going to say anywhere from 1.2 to 1.6 ppm, depending on so all these are ppm, right, when we're talking about this. And then a tertiary, so, oops, I meant to make that an R. And we have a C with another R, right, and a third R. But if this had an H here, so we had a tertiary hydrogen, that one would probably be 1.4 to 1.8. And keeping in mind, hydrogens are partially positive, so there is some inductive effect towards the carbon. So we're the carbons can slightly deshield the hydrogens. The more carbons we have surrounding, the more slight deshielding we can have occurring. And then the next jump up would be, what if I have a carbon double bonded to a carbon, and the carbon next to that had a hydrogen? So not a hydrogen directly on the alkene, but a hydrogen 1 carbon away from an alkene, because this is an electron withdrawing group to a slight extent. I wouldn't say to a great extent at all. And if we got here, we'd say we're probably 1.6 to maybe 2.2 or around there. All right, so then the next one, the next common one, and I'll probably delete after this, so go ahead and write this down or pause the video if you need. If I have a, what we would call a methyl ketone or any sort of R group on the side of a C double bond O, now we're starting to up the game in terms of the electron withdrawing capacity. So in this point, we're going to have anywhere from 2.0 for these protons here to, I'm going to say about 2.4, 2.5. Okay. Continuing, we've got, let me clear this here. What if I have a ring, a benzene ring, and I've got hydrogens not directly on the ring, but if they were attached to a carbon that was attached to the ring, right? So these hydrogens right here that are directly next to an aromatic ring. Those are going to feel some effects. They'd probably be anywhere from about 2.4 to maybe 2.8. Okay. And these are, you should understand the relative sliding scale of this based on your electronegativity and your deshielding effects, but these are just something that comes with practice that you want to get. Okay. So this hydrogen here, if we have a terminal, now we're directly on this alkene. Okay, so in that case, I'm sorry, the alkyne, I should say, this is going to be 2.5 to 3, somewhere in that range. All right, the next one we would talk about would be if I have these next to a halogen. So what about these guys if they're directly attached to a halogen? Well, halogens are pretty electron withdrawing. So now we're talking probably anywhere from the very high 2s, maybe a 2.8, all the way up to, I'd say, probably at least a 4.0. It depends on what you have. If you have a fluorine, you'll be on the higher end. If you've got an iodine, you'll probably be on the lower end, right? And then we've got, what if I have these H's here that are attached to or next to an oxygen, right? So something like this, or I could say, what if I have them directly next to an alcohol? So we're talking about these H's. The alcohol H we'll talk about in a second. That's separate. So these would appear anywhere from probably, we're getting higher up here, 3.3 to probably 4.5. Okay. The next big jump that we would see would be if something was directly on an alkene. So remember before there was an extra carbon and then the hydrogen. Now if the hydrogen is directly on the alkene itself, the vanillic ones like this are going to go from probably about like a 4.7 all the way up to a 6.5. They can get pretty high. And then along those lines, the aromatics are very easy to pick out because they're the only ones that occur up in this region, pretty distinct. You can get them anywhere from, the lowest would probably be about a 6.5 where these guys leave off, and they can go all the way well up to 8, sometimes a little past 8 ppms. Now, a couple of special cases here. If you have the aldehyde, so we're talking about the proton directly attached to the carbonyl. We're not talking about, let me draw over here, this guy, right? This is different because there's another carbon there. We're talking about a proton directly attached to the carbonyl for an aldehyde. These show up as very nice single peaks, and they're usually going to be found in a pretty narrow range, but it's about 9.7 to 10 ppms. Okay, very easy to find aldehydes on NMRs. And then what if you have, so here's the sort of the other two groups we were interested in. What if I have a carboxylic acid, so this is directly attached to this alcohol? All the electron withdrawing stuff over here, the deshielding that's going to occur, this guy's going to be really high up. So we're talking 11 ppms to 12 ppms, anywhere in that range. And then finally the last one. Okay, so take a second to write that down, pause the video if you need. The last one we would talk about would be, what if I have the actual proton on the alcohol or a proton on an amine? Right, so we're not necessarily talking about these R's, we're talking about these guys, these actual protons on the alcohol or the amine functional group, those are very wide ranging. You can get them as low as about 2.5. I've seen some even go a little lower than that, but you will have them range all the way up to 5 most of the time. Okay, and these guys will appear, so a lot of times when you see your NMR, you're going to see these nice large peaks for a lot of the hydrogens with the carbons, and then you're going to see sort of this little nub of a peak like this, and that tends to be that's a result of some of the hydrogen bonding and other effects in the solvent that you can get with these OH groups, NH groups, and things like that. This is still a valid peak, but they're a little more difficult to pick up on some of these. So that should help explain, and we will tie this together when we do some practice, but that should help explain chemical shift and why we see certain things in the different places that we do, right? So if I were to draw a very general molecule here, right? Let's say I draw CH3, CH2, OH, which is ethanol, drinking alcohol. So CH3, CH2, and then the H on the O. So if this is 0, and this is, we'll go ahead and call this 13, right? Where would I find these? Well, this one, and you should be able to follow along, this is 2 removed from the OH, so it shouldn't feel the effects too strong. The general region for this is going to be somewhere between 0.7 to 1.3. Because there is an electron withdrawing group 2 spaces away, I'm going to go ahead and call this, let's go ahead and say it'll be about a 1.1. So I would find a signal here. Now, for those of you that may have seen other NMRs, yes, there is splitting, but that's going to be a separate topic, so we're not talking about that right now. We're just showing where the signals would appear, okay? So yes, this would be a triplet for those of you that are looking for that sort of stuff, and we'll do that in a different video. All right, so the CH2 here is directly next to the OH, and so that's going to get pushed up quite a bit. So we could say that this, we could estimate, might be around, we've got a somewhat of a large range. We said probably around like a 3.3. And again, these are general ranges to a 4.5. Okay, so we could probably find that maybe around 4.0. I'm taking very wild estimate here. But this is the general concept is what you're looking for here, right? So this would be the CH2 signal. This would be the CH3 signal. And then this guy could show up anywhere in between. So we'll go ahead and we'll say maybe, let's go ahead and put it at like a 3.5. We would see our little OH signal. Okay? And so we'll actually practice some examples. We'll talk about some of the other stuff. But the general idea here is to understand downfield and deshielding, upfield and shielding, and the general effects of shielding and how those play in to chemical shift. So I definitely am going to cut it off there because we're looking at close to a 23-minute video for this. Probably the most difficult concept. Splitting can be sometimes, but we'll talk about that when we get there. So I will see you guys for the next lecture, which is going to talk about integration, and that one should not take quite as long. So thank you very much. Please remember to like, comment, and subscribe if you found this helpful, and I am there for you. I will see you guys next time for the next lecture. Thanks for learning with me.